Okay, click and close. I want to just review a couple things with you. I'll give you a little time to work today. I've got a, so I don't want to do a lot. I want to maybe go through a quick example of how to deal with a certain kind of problem that you're going to see on your homework. And then I want to look at slant asymptotes. I'm going to give you a short review assignment, really. But it'll incorporate the stuff we've been talking about also. So the questions on there would be if you're looking at rational functions, things like find horizontal asymptotes, find vertical asymptotes, and if there are no horizontal asymptotes, then is there a slant asymptote, which sometimes people call an oblique asymptote. And I think in the language of the textbooks that I had to steal these questions from, the online text, I think they say oblique asymptote. Same thing, right? So before we do that, though, one of the tools we're going to use is synthetic division, which you're well accustomed to. But I want to make sure you know how to deal with situations like this with synthetic division. So if I wanted to simplify this quotient, I wanted to divide out these polynomials. So I'm simplifying a rational function here. What are my options? How can I divide polynomials? I can use long division, right? And that's sort of the default. I mean, long division always works. It's just a little bit of a longer process. Now, when can I use synthetic division as a really nice shortcut? Okay, so when the bottom is linear, right? And when I can write it in the form, here's a way you can think about this. So I can use synthetic division when I have something like p of x, where p is just some polynomial, divided by x minus a, where a is just the zero of the denominator. A could be positive or negative. So if it's negative, it would look like a plus. If a is negative 3, it'd be x plus 3, right? But the bottom has to be written in this form. It has to be written in the form x minus a number, a real number, so we can identify this as the zero of the denominator, right? Okay, so then this isn't in that form, right? Do you remember doing problems like this, like in Algebra 2 or maybe last year, where you're trying to use synthetic division on these? Okay. And you may not. You may not have ever done this before. If you haven't, it's no big deal. I want to show you how to do it. What could we do? This doesn't match the form. This is not compatible with synthetic division at this point right here, is it? Okay, what would I have to do? Yeah, and you can think about that in two ways. Probably the most correct way of saying it is you'd factor a 2 out of the bottom and the top, right? But it'd be the same thing as long as I'm multiplying by 1. I'm not changing the form of the value of this expression, right? So the other way to think like that is I could just distribute a 1/2 through the top and the bottom, treat both equally. If I do that, what am I going to get? If I were to and you guys understand that's the same thing as factoring a 2 out of the top and the bottom and just canceling the 2's. Yeah. Very same thing, right? So what do I get? On the top I get
2x plus x minus 1.
Okay. On the bottom?
Okay.
Okay, everybody agree? Okay, and then I could just do synthetic division on that. Okay, that's now it fits this form. So if I were going to use my synthetic template, what do we end up with here? So my synthetic template is going to look like, what are my coefficients?
2, 0, 1, 1/2. Oh, negative 1/2.
What's my 0 of the denominator? Okay, and then we just go to town. Right? Pull this guy down. 2 times 1/2 is plus 0. 1 times 1/2 is 1/2 plus 1. Okay. 1/2 times 3/2 is
3/4.
And negative 1/2 plus positive 3/4 would be,
1/4.
okay. Now, so what's that tell us then? That tells us that this is equal to, this whole thing is equal to what?
2x.
2x
squared
plus x plus 3/2. And the best way to do that is always to work backwards. You know that this has got to be the constant, coefficient of x squared, coefficient of x cubed, etc. Right? So we end up with 2x squared plus x plus 3/2, right? Plus 1/4 divided by what?
X minus 1.
Are you recording?
I am. Good thing you checked. Okay, and so this is pretty goofy here. What would I do to the top and the bottom here maybe to make that look a lot better?
Multiply by.
Multiply by 4, right? Because I've got a 1/4 on the top. So I want to multiply by the least common multiple of all the denominators. So if I multiply top and bottom by 4, then this starts to look a little better. Then I end up with 2x squared plus x plus 3/2 plus 1 divided by 4x minus 2. Okay, get the idea? Okay, so whenever we do synthetic division, we always have to make sure that the coefficient of x on the bottom is 1, right? So then let's go back. We were working on a problem yesterday, right? And we had gotten down to where we found that, what were we doing here? Oh yeah, we were using the rational root theorem. Right? We're trying to find the zeros. So let's kind of recapture where we were. We were trying to find the zeros of this expression right here. We're solving this equation where 2x cubed plus x minus 1 equals 0, right? Rational root theorem, remember, tells us that all rational roots have to be built from factors of the constant divided by factors of the leading coefficient. And so we didn't have many options. The factors of the constant are just plus and minus 1. The factors of the leading coefficient are just plus or minus 1 and 2. And so we're just going to whittle these down. We're going to try the easiest ones first, and we're going to just go through synthetically until we get a hit, until we get a 0 remainder, right? And so we tried both plus and minus 1, neither of which worked. And so now we're on to plus or minus 1/2. Can we do the 1/2? Yeah, we can. We can do that, but you just got to recognize what you're, kind of the relationship between, if I'm using these types of fractional zeros, how I might end up having to simplify my answer, right? Like we did in the last example. We multiplied top and bottom by 4 and made that thing look okay, right? So if we run a 1/2 through, let's try that. So we pull down the 2, right? 2 times 1/2 is 1 plus 0. 1/2 times 1 is 1/2 plus 1 is 1/2. It's not going to work, is it? Nope. You can already see that's not going to work. So if there is a rational 0, it's got to be negative 1/2. Does that work? Oh, that's not even in our domain anyway, is it? Okay, so there are no. Oh, you know what? We messed up.
Oh.
No, we didn't. We're good. We're good. 2x cubed. It didn't work. Yeah, I thought that one would for some reason. 1 plus 1. It's not. There aren't any. So the answer, right? So the answer is not rational. So then, what do you? I mean, that leaves you in the lurch a little bit, doesn't it? So what do you do? The rational root theorem. There's the weakness of the rational root theorem. It's only going to give us the rational zeros of a function. So how do you find the irrational zeros? Unfortunately, you need calculus, there's a little trick, which I may or may not show you guys this year. It just, if we have time, I'll come back and do it at the end. There's a little trick called Newton's method, which allows you to use this recursive routine to go in and find, you don't get them exactly, but you can get them with arbitrary precision. You can find the irrational zeros that way. So we may or may not see that. Who knows? Maybe, maybe not. Okay, so what I want to do today, I want to just take a look. Let's take a look at some slant asymptotes, right? So if we're trying to find, our goal now is we want to find all the asymptotes of these functions, okay? So are there any vertical asymptotes? At 2. 2 is a vertical asymptote. How come? Bottom is 0, but the top is not. It's a unique 0 of the denominator. So we have a vertical asymptote at x equals 2. Okay, is there going to be a horizontal asymptote? What's the consensus? Is there going to be a horizontal asymptote here?
No.
No, you're right. There can't be. And how come?
Bigger than the
Top's bigger than the bottom, right? We only get horizontal asymptotes when the bottom polynomial is a higher degree than the top, right? In which case we get the horizontal asymptote y equals 0, right? Or if they're equal degrees, and then we take the ratio of the leading coefficients, right? We get y equals the ratio of the leading coefficients. Remember those 3 types. But the third type was, if the top is a higher degree than the bottom, then there's no horizontal asymptote, right? But we can do something else. If the top is 1 degree higher than the bottom, can you tell me just in general terms what has to happen when I divide it out? What's going to be the degree of the result if I divide it out? If I'm dividing, in this case, a quadratic by a linear. Okay, good. You're going to get, it's going to be linear, isn't it, right? You're going to get something of the form mx plus b plus maybe some remainder. Everybody see that? Okay, so if the numerator is precisely 1 degree higher than the denominator, you always know that you are going to get a slant asymptote. You're going to get an asymptote that is not horizontal nor vertical. It's going to be on some, that's on a slant, or it's going to have some slope to it. So we can find those pretty easily. Like in this case, what would we do? This is a pretty easy one. We divide them out using what, for sure? Synthetic division, yeah. What are our coefficients on the top? 3, 0, 0. And on the bottom? 2. So we get 3, 6. But really, who cares, right? We don't care about that part, because if we write this out, then what that's telling us is that f of x equals, and you'll see this, f of x equals 3x plus 6 plus 12 over x minus 2, right? Now, if we take our limit now, if we take the limit of f of x as x approaches plus or minus infinity, what am I getting? The limit of 3x plus 6 plus 12 divided by x minus 2, that whole thing, as x approaches plus or minus infinity. Well, what happens to this part? Where the top is a constant and the bottom has an x in it. If I take the limit as x goes to plus or minus infinity, what's happening to that term? It's going to 0, isn't it, right? Top staying at 12, bottom is going to infinity. Regardless of sign, that goes to 0. And so what's left behind? 3x plus 6, right? So that is the equation of my oblique or slant asymptote. Okay? So when you're going through this process, if you know you're trying to identify a slant asymptote, you can stop. Why waste time? You can stop right there, can't you? Right? I mean, unless you're trying to show all your work, in which case, you want to see that, you want to show that part. But if you're just trying to find what the slant asymptote is and get the job done, you don't even know what the remainder is, because you know that's the term that's going to go to 0. Okay? graph this thing? Let's just graph it. So we end up in so we get slant asymptote at y equals 3x plus 6. Oops. Gotta go fix that squared. All right, so there's my function. What happens if I zoom out? Okay, we see a couple things. Well, we see if I graph these lines, what if I graph the line x equals 2? There's my vertical asymptote pretty clearly. If I graph the line y equals, what was it again, 3x plus 6?
Yes.
Well, you know, right? There's my slant asymptote, okay?
One of these days, my whole thing.
Okay. So then what would we do about something, let's skip up, that's just synthetic division, right?
Yeah.
Okay, we don't, you know how to do that. Okay, what about this one? So do we have to, how are we going to divide this one out? Could use long division. Can anybody find a better way?
Just factor out x squared out. Or no.
Long division, of course, is going to work, but there's something unique here. I just want you to kind of spot this pattern because this saves you a lot of time. What do you notice about the denominator here that's significant? It's different.
X squared.
Yeah, it's a monomial, right? Single term in the denominator. If you have a single term in the denominator, that's a common denominator, right? Why not just split this up and break the fractions apart? And so this equals 6x cubed over x squared minus 7 over x squared. Look how easy that is then, right? You always want to take advantage of that. If you're simplifying a quotient where you have a monomial, yeah, don't ever bother dividing, right? Just break it into fractions and simplify each fraction. So then this is just going to become, what, 6x? And this is minus 7 over x squared. So if we take the limit of this function, pretty obvious what's going to happen. The limit of that as x approaches plus or minus infinity, well, what's happening to that?
0.
And so the limit is 6x. So there is your slant asymptote, just 6x. Right? Okay? Okay, what about one like that? But you only have really one option this time. Yeah, this time you have to use long division, don't you? Okay. So it's been a long time. Let's maybe review one long division problem just so it's been a little while. So we're going to set up polynomial long division. Right, you get your
That's so sad. It's kind of gross.
what goes where. We write out our big division bracket. What goes inside, what goes outside.
The top goes inside.
Top goes inside. Okay, so tell me, am I writing this out okay?
No.
Okay, you're right. What did I do wrong?
You need
Do
0.
all the ones and make them.
Good. You have to preserve, you must preserve in long division a column for every power of x, right? Because it's a process of subtracting terms, and you can't do that if you don't have a column for every power of x. Okay?
Big sadness.
So we've got to add this 0 coefficient for x to the 5th, a 0 coefficient for x to the 4th, 0 coefficient for x cubed, x squared. You get a 0 coefficient for x, and then finally we get a plus 2. Okay, what about what's out front?
You can just leave it like that.
Okay, that one I don't have to mess with adding all the 0 coefficients there, because that's not where I'm doing the vertical subtraction, right? So out front I can just have my x to the 6th plus 1. So you guys got this. And then, how do I determine the first term in the answer? Yeah, I'm just taking quotient of leading terms, right? So x to the 7th divided by x to the 6th. If I do that, if I do x to the 7th divided by x to the 6th, well, what is that? So x is my first term. And then once I get a new term on the top, what do I do? Good. I distribute it through because I'm multiplying and subtract. So I'm going to get an x to the 7th plus x. I strongly recommend you put the whole thing in parentheses and the subtraction sign out front. So then you always know that the kind of the mode you're going to get in is going to be top minus bottom, right? All the way through. And then you don't. When people distribute the negatives, it just seems like I always see people make more mistakes that way, right? So you're just going to go x to the 7th minus x to the 7th cancels. This pops straight down. 0, 0, 0. X squared. What's 0 minus x? Right? Okay, and then next term. And you get 2 on it. 2x to the 6th divided by x to the 6th is my 2. I can distribute the 2 through. 2x to the 6th plus 2. You're going to subtract the whole thing. And honestly, who cares at this point, right? Because whatever I get from this point is going to be the remainder, which is going to get extinguished when we take the limit, right? So our horizontal or our slant asymptote is at y equals x plus 2 this time. Okay? Are there any vertical asymptotes?
Negative 1.
No. Be positive, chief. There's no.
Oh, yeah.
I don't believe.
Okay. Now, you're all going to get the answer, but I want to make sure, I want to help you articulate that in a way that's going to sound good, and it's going to make sense logically. So are there any vertical asymptotes?
No.
Okay, why not?
Because it's even power.
Because it's what?
To an even power.
It's to an even power, right. So there are no zeros of the denominator, and we know that because x to the 6th plus 1 is always positive valued, right? Does that make sense? X to the 6th is non-negative, and a non-negative number plus 1 is positive, right? So we're going to get no zeros in the denominator. So we're done. We don't have to, this would be another case where it'd just be long division, right? Okay, so 2 things. Before we jump onto something else, what about, I'm just going to make one up. What about, I had something like,
X squared plus 7 divided by 6. He just asked me to shut up.
okay. What are you eating? Okay, let's take that one. Are there any vertical asymptotes?
Yes.
Okay.
1.
At 1. And you know that's not a whole, how come? Okay, because the value of the top at x equals 1 is not 0. Good, so it's a unique 0 at the bottom. You get a vertical asymptote at x equals 1. No horizontal asymptotes, obviously. Are there any slant asymptotes?
No.
No? Okay, but I want to show you something, and this is like way above the scope of like just a first year calc class, but it's a cool concept. It's a really cool concept. What if I wanted to be able to do something similar to what I did with the slant asymptote? If I divide this out, this is synthetic, it's quick and easy to do. What do I get if I divide this out? do it real quick. What are my coefficients?
0, 1,
And out front?
1.
So we get, bring down the 1. 1 times 1 is
1, 1, 1. Oh, JK.
right, and then 2, 1. Okay, so f of x then is equal to 2 parts. It's equal to x squared plus x plus 2 plus 1 over x minus 1. And if I take the limit of f of x as x approaches plus or minus infinity, that's going to go away, isn't it? See what I'm saying? So I'm just going to get x squared plus x plus 2, right? Okay, what if I graph this thing? What's significant about that? It's a parabola. Okay, is it going to show up in my graph?
I assume you'd be showing it because it would show up.
You're right. 'Cause why else would I show it to you?
So I would say yes.
So if we go back and we graph this original function, x cubed plus x minus 1 divided by x minus 1. Okay, let's turn that guy off. Well, there's what we get. Okay, so that's what we get. That doesn't look, I don't see any parabolas there at all, right?
You're right.
But as I zoom out, look what happens. Let's tweak the, whenever you've got a function where the top is a lot bigger than the bottom, the thing is going to grow vertically a lot faster than it grows horizontally, right? And so when you want to get a good graph of this, typically you want to kind of slow down the x-axis growth and make the y-axis growth get bigger. So if we go up here to the little toolbar where I can set the size of the window, what if we just went like from -10 up to +10? Okay, now how about if I just zoom out from there? Well, what are you starting to see now? Like if I superimpose that parabola that we had, what was it again? X squared plus x plus 2? What do you know? So that parabola does start to show up. Is it an asymptote? No, it's not. An asymptote by definition is a line, but you might call this an envelope. This function is going to fit this parabolic envelope as you get far away from 0 in the x direction, right? But what does it do? It still tells you what the large scale behavior of the function is. What's the point of an asymptote? It doesn't tell us what's going on in here at all, right? That's not its job. Its job is to tell me what's going on the tails of the function. And if I zoom, I've already zoomed out far enough. If I zoom out a little bit, I mean, the two are indistinguishable once you get far away from 0 on the x-axis.
Yeah.
So it still is a pretty cool thing. It tells me the end behavior of the function, right?
Yeah.
Okay. All right. Last little tidbit. So on your homework, there is a problem like that. So let's just take a second and let's talk about this. Not that this particular problem is such a big deal, but this is sort of a class of problems that it's nice to know what to do with. If I'm trying to evaluate these limits, like as x approaches 0 from the left and 0 from the right, if I try to plug in small negative and positive values, I want you just to see what happens to this thing, why it's not very descriptive and it's confusing. If I try to leave it the way it is, and we evaluate this at 0 minus, for example. Okay, so as x approaches 0 minus, what is f of x looking like? Well, on the top, as I approach 0, what's anything to the 0? 1. So on the top, I'm just going to get 5 plus 7 is 12. That's unambiguous, that's easy. But the bottom, what's happening on the bottom? On the bottom, I'm getting e to the 0 looks like 1, right? And e to the 0 looks like 1. Well, it's approaching 0, but it's very difficult to tell, is it a small positive or negative value, right? When you've got terms that are being added. If I plug in a small negative there, I'm going to get e to a very small negative minus e to a very small negative. That's hard to tell, right? Anytime you have indeterminacy like that, 0 minus 0, that's very difficult to deal with. Okay, so what's a better option here then? Factor it, right? If I can think about, instead of having a sum of terms on the bottom, if I can think of the bottom as being a product of factors, it's much easier to establish what the overall sign is, right? We know that the product patterns for signs are simple. Negative times negative is positive, etc. So what if we were to factor this out then? Let's try that. So we've got our f of x. What would maybe make sense to factor out? And there's no really one answer, but we're focusing on the bottom really, aren't we?
E to the 3x.
We could factor out an e to the 3x. That'd be fine. Okay, let's do that. So if I factor out an e to the 3x, let's do the bottom first. What am I left with? 1 minus e to the
X.
Okay, everybody good with that? Okay, so we're just dividing away an e to the 3x. On the top, what are we left with? What's e to the x divided by e to the 3x? E to the negative 2x. Right? If I divide like bases, I subtract the exponents. We good with that?
Yeah.
Okay. E to the negative 2x. And you can also ask yourself, I do it this way a lot of times. I'll just say, well, e to the 3x times what is e to the x? Negative 2x. Because when I multiply like bases, I'd have to say 3x plus what is x? Negative 2x. Right? And then plus 7 e to the x.
Did you just forget the 5?
What'd I forget?
The 5.
Oh, the 5, yeah. Okay, and then algebraically, those would cancel, right? So then if those cancel algebraically, what do we end up with here if we try to evaluate this thing now? So if we're evaluating this at 0 minus, on the top we're still getting our 12, right?
Yeah.
On the bottom we get exactly 1 minus e to the x. Now if we're approaching 0 from the left, right, think what that looks like in terms, but we have to actually think about how the function behaves. This is where we might want to just take a second and let's sketch what the exponential function looks like. If that's 1, what's the function doing? It's going, right, starting, it's asymptotic on the negative x-axis, and then it starts to grow through the point 0, 1, right? And then it just increases more and more rapidly. So as we're approaching x, or 0 from the left, we're over here walking towards that point, aren't we? So the y value is going to be 1 minus or 1 plus? 1 minus, isn't it, right? So we've got 1 minus, 1 minus. So what's that going to be then? We end up with positive 12, exactly 1 minus 0.99999 is what? 0 plus. And we got it figured out. See what I'm saying? Okay? All right. Then we can do the same thing for 0 plus. What about, could we have, is there anything else we could have reasonably factored out? Because I just want to show you that there's, you know, it's not like there's just one way to do this. It's just the concept of what you're trying to accomplish, and it's going to work.
Maybe we could have factored out e to the 4x.
I could have factored out e to the 4x too, couldn't I? Right, what would have happened if I would have done that, if I factored out e to the 4x?
What is this guy doing? He wants to smack that.
down yesterday.
I got my video.
Like some super creature that was
Bro, imagine the super creature saying that sentence.
Mongoloid. Mongoloid. I forgot. And then he said I wasn't genuine, and then I sent him a picture of me with the definition of genuine.
Oh, there we go.
Okay, I gotta build